Hello everyone, today let's take a look at Quantibuzz number 40, a super simple sets question. So we're at a tech expo and we have 1,000 visitors who could try either of two demos, a VR and an AI demo. And it tells us that 600 tried the VR, 550 tried the AI, and 200 visitors tried neither. So it's asking us how many tried both. So making a Venn diagram is going to be super useful in understanding any of these sets questions or even any of the conditional probability questions, and we'll use them a lot. So this box on the outside is always going to represent the total population, which means in this case, well, we have 1,000 total people. So there's going to be 1,000 people enclosed within this box, right? Now, similarly, the number of people who try the AI demo will go within this bubble here, and the number of people who try the VR demo will go within this bubble. And obviously we have some overlap, and being in here just means that you tried both demos, and then we have some space outside of either of these bubbles, which means you tried neither of the demos. Okay, so now what information is the question giving us? We have 1,000 total visitors, right? 1,000 people within the box, 600 visitors who tried the VR demo, which means we're going to have 600 people within the green circle, and 550 who tried the AI demo, which means we have 550 in the blue circle. Now we have 200 who tried neither, so 200 out here. And what's it asking us? How many visitors tried both demos? So that's just going to be the intersection between A and V. Okay, so how are we going to solve this? Well, it's super simple. We have 1,000 total people. We have 200 who tried neither. So what does that mean? Well, that just means that we have 800 people, right? 1,000 minus 200 who are within any of these two circles here. Okay, so what does that tell us more formally? Well, it tells us that the magnitude of the union between the sets A and V is equal to 800. So these bars mean magnitude, and this union means that we're going to take everything that's either in the set A or in the set V or in both. Okay, now here comes the inclusion-exclusion principle, which is probably the formula that we're going to use the most in both combinatorics and conditional probability and in sets. Okay, so here's the generalized form of inclusion-exclusion, which again, we're going to use a ton in sets, conditional probability, combinatorics. We're going to end up proving it in the combinatorics section of the roadmap, right? So you don't need to know it all right now, but basically what it's saying is if we take the union of the magnitudes of a bunch of sets, well, that's going to be equal to the sum of the individual magnitudes of all these sets minus the sum of the double intersections between all of these sets. Then we add on all the triple intersections and we subtract off all the quadruple intersections. Then we add on all the quintuple intersections, and you'd go on, etc., as an alternating series. Okay, now back to our case, which is going to be really simple, right? We're trying to find the magnitude of the intersection between two sets. Okay, so first let's plug our numbers into this formula to understand how it works, and then let's actually think about why the formula works. Okay, so first of all, we already know that the magnitude of the union is 800, so if we just plug into our formula, right, we know that the sum of the individual contributions, which are going to be our 550 and our 600, right, so we're going to plug in 550 plus 600. Okay, so now for our next term, we're going to subtract off the sum of all of the double intersections between all of our sets. In this case, we only have two sets, so there's only going to be one double intersection. And in our case, this term is what we're actually trying to solve for, right? The number of visitors who tried both demos. So let's subtract that off, right? The magnitude of intersection between A and V. And obviously for all of these future terms, they're going to be 0 because we don't have any possible triple intersections. We only have two sets. And then obviously when you solve for A intersection V here, you're going to wind up with the magnitude being equal to 350, which will be our final answer. But now why is this true? Why did this equation work? Okay, the reason is when I'm trying to calculate the union of a bunch of sets, I'm trying to calculate everything that lives within them one time, right? So I want to count everything over here once, and then I want to count everything over here once, and then I want to count everything over here once, and I just want to sum these three up, and that'll give me the union. But that's not what we're given, right? We're given 550 and 600. So when I sum these up, the magnitudes of the individual sets, notice that we're just going to be overcounting this intersection. And that's because the magnitude of this white part here is both included in the number 600 and the number 550. So when I sum up 550 plus 600, what am I doing? Well, I'm taking the magnitude of this orange part plus the magnitude of the white part, and then I'm taking the magnitude of the salmon part plus the magnitude of the white part again. But I only want to count the white part one time, right? And I'm counting it twice. So what do I need to do? I need to subtract off the magnitude of the white part, which is just the magnitude of A intersection V. And now I'm just counting each part one time, which is what we want when we're calculating the union. And this right here is just this part of the equation, and this here is this part of the equation, right? So again, we're going to look at this more in the future, especially when we prove it, but the whole gist of this whole equation is that we want to count every single region within here one time, and it's going to get a lot more complicated when you have more sets. But basically all of these terms are just going to be accounting for some amount of overcounting or undercounting, right? So when I do these, I overcount, so I subtract off some term. And then when I do that, I undercount, so I need to add back on some term. And then I overcount again, so I need to subtract off this term, and it goes on like that. Yeah, so I don't know why I ended up talking about that for so long, but basically this problem was super simple right here. But when we go on and do the future problems, it's going to get complicated, so I just wanted to talk about it first.